All right, so this is part two. Um, we are going to be talking about the two-factor ANOVA stuff now, right? So with two-factor ANOVA, this is where we have two different things we're testing at the same time. And actually, because we have two different things to test, we end up with three. This is how it's going to work. We're going to have these two different factors that we're testing at the same time. And, this is kind of like what we do with regression. With regression, we're testing multiple factors at the same time. And with multiple regression, we can do interactions and all sorts of stuff like that. So this is another way to do these multiple factors. And when we have these multiple factors, right, we're talking about two different variables, each of which is a categorical variable, right? So the example here, they have gender, male, female as factor A, and then level of violence, non-violent versus violent as factor B. And we are seeing how those two categorical variables affect a response variable, which is like a scale variable, like a continuous variable, generally speaking. Although it doesn't have to be continuous, right? But it's not categories. It's going to be, it could be, a scale from 1 to 10 or whatever. But it's something where we can use that as a response the same way we would and look at differences. Right? So if your factors A or B are not categorical, then this is not the right test, right? Then you need something more like regression or something like that. But when you have a categorical and another categorical, these are your two, and they're basically independent variables, right? These are your independent variables, and you're seeing how they affect a dependent variable, right? And in this example, the dependent variable is scores ranking aggressive behavior, right? So you want to know, does aggressive behavior depend on the violence level of the video game that the people are playing, right? They can play a non-violent game or a violent game. And does it depend on the gender of the player, male or female? And that's what this example is going to show. So we're seeing, does factor A make a difference? And that's going to be one hypothesis test, right? Either gender makes a difference on aggression scores or it doesn't, right? And then level of violence, right? Does playing a more violent video game have an effect on aggression scores? Yes or no? Those are going to be the two main things we're testing. Okay, so we have four different groups, right? We have to take our subjects and break them into four different groups. We have the men who are being split into non-violent and violent games, and we have the women who are being split into non-violent and violent games. Okay, and so we have these first two tests, which is what I already mentioned, right? What happens to the level of aggressive behavior when the violence is added or taken away? Is there a difference in aggressive behavior for male compared to female participants? And then there is naturally this third thing that comes up that we can test, which is that is aggressive behavior affected by specific combinations of game violence and gender? And we call this an interaction. All right, an interaction is going to be where specific combinations end up looking different than you would expect just from the factors alone, right? So maybe you have a case where violent video games do increase aggression levels, and you might have a situation where men generally have higher aggression levels than women, but maybe one specific combination, right, like women playing violent games, is higher or lower than you would expect just based on the information you have about the factors alone, right? And so that would be called an interaction, right? Then what you would say is that, the difference between non-violent and violent games in terms of aggression levels depends on whether the player is male or female, and these two variables interact. Okay. And so all the tests, all the hypothesis tests are going to be done by looking at the variance, that is the differences between the treatments that we're interested in, divided by the variance if there was no treatment effect. So when we're looking at factor A, we're going to look at the differences between the four groups, and then we're going to divide by the differences that we would expect to see if factor A made no difference, but we still had factor B. Right? And then for factor B, we'll do the opposite. Right? We'll do the variance between all four groups, and then we'll divide by the variance that we would expect to see if factor B had no impact, but factor A still did. Right? And then for the interaction, we would do the variance we would expect, the variance between all the treatments divided by the variance we would expect to see if we had both factor A and factor B working as we know they are supposed to work from the data, but without interactions. All right, and this, if the interaction thing is still not totally clear, don't worry, we've got some nice pictures further on that's going to help you understand. Okay, so we have these three tests, like I keep talking about, right? The first test is on factor A. The null hypothesis says that the mean for group A is the same as the mean for group A2, is the same as mean for group A3, is the same as, etc. The group mean for every group grouped by factor A. Right? So in this case, factor A was gender, male versus female. So the null hypothesis just says like aggression levels are the same on average between men and women. That's the null. The alternative says they're not. They're not the same, they're different. Factor B's test is the same, but for factor B, right? The null hypothesis says in our example that whether a video game is violent or non-violent has no effect on aggression levels. And the alternative says, yes, it does have an effect. Okay, and then the interaction test says there's no interaction is the null, and there is an interaction is the alternative. And we don't write this in terms of like mean 1 equals mean 2 or anything. We just write there is an interaction versus there's no interaction, right? And the null hypothesis is always that there is none, right? That's what makes it the null hypothesis, right? The null hypothesis says there's nothing to see here. Okay, so here's the pictures I talked about that are going to help you understand interactions a little bit better. In the first picture here, we can see that the scores for men are higher than the scores for women. The red line is always above the blue line. We can also see that the scores for violent video games are higher than the scores for non-violent video games, right? The lines go up when you add violence. And that's true for women and men. And the lines go up by the same amount, right? So when we add violence, that adds the same amount to women as it does to men. The lines go up the same amount. And that's because we have no interaction here. The effect of gender and the effect of violence can just be separated out. And we can say, all right, so men have scores about 4 higher than women, right? The difference between here and here is 4, and the difference between here and here is 4, right? So no matter what type of game they're playing, men score 4 points higher than women. And also, no matter what gender you're looking at, adding violence adds about 1.5 points. We're going from 7 to about 8.5, or from 3 to about 4.5, right? And so that doesn't depend on gender, right? So the difference that you see based on gender doesn't depend on whether the game is violent. And the difference you see based on violence doesn't depend on the gender, right? They have no interaction. And you can separate them nicely. And that visually, that looks like these parallel lines. The second example, we do have an interaction here. Because what happens is, if we look at men versus women, yeah, men have higher aggression scores than women. And if we look at violence, we can see that overall, violent games tend to have higher scores than non-violent games, but that effect depends on gender, right? Because violent games are making the men's aggression scores go way up by like 4 points, and they're not actually changing the women's aggression scores at all, right? So the effect of violence, which does exist in this graph, right? There is a violence effect, but the violence effect depends on gender in this second picture in a way it did not in the first picture. In the first picture, the violence effect was the same for both groups. In the second picture, it's different. And that's what we mean by there's an interaction. There's an interaction. Some and these two variables, these two factors, cannot be neatly separated. We can't just say violence does this, gender does that, and then just plug them in and get our answer, right? We have to say violence does this for men, and violence does that other thing for women. All right, and it's a little bit of a more complicated picture because they can't be separated. Those two factors are interacting and they're stuck together. Okay, and so that's the picture that's going to explain like what does it mean to have an interaction. Right, and of course this would be the same idea if you had like more than two groups, right? I can draw a little picture here, right? Like if I draw just a little graph here, and I have like group 1, group 2, and group 3, and then I have, you know, men and women again, let's say, and I have this picture for men, and then I have this picture for women, right? This is a no interaction picture, right? Because the men and the women follow the same shape, they're just shifted. Right? This is no interaction. All right, we have one variable which makes things go up or down, and we have our second variable which makes things go up or down, but they're separable. We can just split them up, right? Whereas this picture, if I do the same thing, right? If men look like this picture, but then women have a different pattern, right? Then there's an interaction. Because they don't show the same shape. Right? Whatever three categories we have here are having a different effect on men than they are on women. All right, so I think that's clear now what the interaction is, right? And so now we're going to be doing this two-factor ANOVA where we have these three different hypothesis tests. And if you look down here in this picture, this is what's happening, right? We have the total variance goes to between and within like usual, right? And if you remember last time we talked about how the within could be split up into between subjects and error, and we would do that for a repeated measures. Right? With repeated measures, it's the within treatments that get split. But for the multi-factor ANOVA, what happens is the between treatments get split. Right? We can say, hey, the four groups are performing differently. We see different aggression scores in those four groups. How much is due to gender? How much is due to violence levels? And how much is due to the interaction between those two variables? We can just split it all up. Okay? And so that is what we're going to do. All right, and so we're going to start with our basic, you know, between versus within, and then we're just going to split the between into these three different pieces. All right, and so for each factor, we're going to have these different formulas, right? Which is going to depend on the total for the row divided by the total number of things in the row, and the total for the column depending on the number of things in the column. So we're going to have these different formulas, which still looks generally like our overall picture where we have the squareds and so on. It's the same type of formula again, right? And then that's going to get us our factor A and factor B, and we're going to do a big example of all of this so you can see all of the math happening by hand. But the interaction term is going to be very easy. The interaction term, we're just going to figure out what's left, right? We're going to already know the SS between, and we're just going to subtract the two factor SS's to see what's left. Okay, and we're going to have the degrees of freedom based on number of rows -1 or number of columns -1. It's going to be pretty straightforward. I think we should just jump into an example and see how it goes. So here is our example. All right, we've got these 4 different groups, right? And we got the raw data. We have 5 people in each group. We have the totals for each group. They're already added up, the totals there. And I'm going to just start squaring these like I always do, right? So 121, 64, 81, 100, 49, 16, 16, 64, 25, 16, 100, 49, 100, 36, 49, 100, 36, 100, 100, 81. And now we can add those up to get the sum of squares for each group. And I know the SS is already calculated for each group, but I'm just showing you how you would do it, right? It's good to have these things reinforced over and over. So 121 plus 64 plus 81 plus 100. And if you're totally comfortable with that part, then you can just jump right ahead. You can just jump ahead a few minutes to after I've calculated these SS's, which are already here. All right, but I'm just going to do them, because some of you will appreciate it. Will appreciate seeing it done again. Okay, so once I get the total, the sum of squares for each, right? I could add all 4 of those up and get this number over here, right? That's the sum, the total sum of squares for everything. And then what I can do now is I can do the SS for each of these, right? So I'm going to do the 415 and the 45 squared over 5, right? So 415 minus 45 squared over 5 is 10. That's the SS here. And then we do the 137 minus 25 squared over 5 is 12. There. Right? And then here we're going to do the 334 minus the 40 squared over 5. And that's going to be 14. And then we're going to do the 417 minus 45 squared over 5. And that's going to be 12. So we get these SS's for each group. And if we add those together, 10 plus 12 plus 14 plus 12, we get 48. And that's the SS within. Right? And then if we do the same thing for the whole thing all together, right? The 1303 minus the 155 squared over 20, because there are 20 people in total, right? 5 times 4 is 20. I'm going to get 101.75. And so with this, I can start making my table, right? I'm going to make a table down here. I'm going to have my SS, and I'm going to have my groups. I'm going to have my between and my within and my total, right? Actually, I'm going to leave a little bit more room for the between, because the between is going to get split. Right? So the between is going to get split into A, B, and interaction. Right? So the within we just calculated was the 48, and the total was the 101.75. And we subtract those to get the between, right? So 101.75 minus 48 gets me 53.75. And this is the thing that's going to get split into these three groups here. Okay. And so we need to use the formulas to find each of these. Okay, so if we want to look at what the formulas were for those SSA and for factor A and for factor B, right? We're adding up, we're going to square the row totals and then divide it by the number in the row. And we're going to do that for each row, and then we're going to add them together. And then we're going to subtract the G squared over capital N. All right, so what does that look like? You see I have the row totals here, the 70 and the 85. If you don't know where they come from, right, it's just the total for everything in this row, everything in the self-regulated row. So the 45 plus the 25 gets me to 70. Right, that's the 45 plus the 25. Right, and the 85 is the 40 plus the 45. Right, and so we can see we have the row totals and we have these column totals. What do we do with them? Well, let me get some color coding going on here, because for factor A, I'm going to be doing rows, right? So I'm going to do 70 squared over 10. Why is it over 10? Because there are 10 people in this row, 5 and 5. And then we're going to do 85 squared over 10, because there are 10 people in the second row. Minus, I'm going to do the grand total of everybody, 155 squared over 20. So let's plug that in and see what we get. I'm going to get 11.25. So I can add that to my table for A here, 11.25. And then I want to do the same for B, which is the columns, right? So let's use green here, right? For B, I'm going to do the columns, right? I'm going to do 85 squared over 10 because there are 5 and 5. There are 10 people in this column. And then 70 squared over 10 because there are 10 people in this column. And you're noticing, hey, look, this is going to be the same number, right? Actually, minus 155 squared over 20. Right, so the last term is the same, grand total squared over overall N, the capital N. All right, and this is going to get me the SSB, which is exactly the same, 11.25. Which means that my final thing, my interaction, what's my interaction? My SS for the interaction is going to be the 53.75, the between minus each of these. Right, so 53.75 minus 11.25 minus another 11.25 gets me 31.25. And so this is my interaction. And now we're going to have the degrees of freedom, and we're going to have the MS, and then we're going to have the Fs. Okay, so degrees of freedom. And if you want to just, pause here and go back and rewind, now might be a good chance, right? We've done a bunch of the math, but this is like the big key important first step. If you can do this, then you're well on your way. The rest of it is going to be easier from here on out. Right? So the degrees of freedom, the total degrees of freedom is n minus 1, capital N minus 1. So 19 within, right? If you remember, what was the within? The within was the n minus the total number of groups, right? In this case, the total number of groups. We're not using just k anymore because we have k referring to the factor A, which is 2, and M referring to the factor B, which is also 2. So we're calling this K times M. But K times M still just ends up being the number of groups, right? So this is going to be 20 minus the number of groups, which is going to be 20 minus 4, so 16. And then the DF between is going to be just the total number of groups minus 1. So the 4 minus 1 is 3. Right? This is the K times M minus 1. Right? And then for the A and the B, it's easy. We just have the K minus 1, right? The number of rows minus 1. So 2 minus 1 is 1. M minus 1, right? The number of columns minus 1 is also 1. And then what's this? This is just going to be whatever's left over to make them add up to 3, right? So 1 and 1 and 1 make 3. Right, so this is going to be K times M minus K minus M plus 1. Technically, that's how you could work that out if you wanted the formula for it. But I never used the formula for that one. It's complicated. I just remember rows minus 1 for the rows, columns minus 1 for the columns, and then this number makes them add up to the total groups minus 1. So these become 1s. Right, so then each of these get divided and get me a numerator. Right, so 11.25 divided by 1 is 11.25. 11.25 divided by 1 is 11.25. Actually, I'm going to keep my color coding. The color coding might be useful to have. Right, so each one of the tests is going to have a different numerator, which are going to be these MS's. But the denominator is going to be the same for all of them, right? The denominator is going to be the 48 divided by the 16, which is 3. Okay, so then we're going to get these 3 different F's, right? 11.25 divided by 3 is 3.75. And then, of course, 11.25 divided by 3 again is going to be 3.75 again. It's the same number, right? But it's for a different factor. And then 31.25 divided by 3 is 10.417. And so these are my F scores. Okay, and now I have my F scores, and I'm going to have critical values to compare them to. Now, in this example, the degrees of freedom for the numerator was the same for all 3 of these, but that does not have to be true, right? You can imagine a situation where you had, for example, let's imagine we had 4 rows and 3 columns, right? Then my degrees of freedom is going to look like, I'm going to have 4 times 3 is 12, so 12 groups, so 11 total between, and that 11 is going to break down into 4 minus 1 is 3 for factor A, 3 minus 1 is 2 for factor B, and then 11 minus both of these, 11 minus 5 is 6 for the interaction. Right? So because we have different degrees of freedom, these would give you different critical values. From the table, right? When we go to our F table, we will look up the critical value, and we would get different critical values for each of these because we would have a different column to look in for the numerator degrees of freedom. Of course, the denominator degrees of freedom would always be the same, right? Because the denominator degrees of freedom just depends on this within thing here, right? That's going to be this fella here. right? The 16, right? In our example, all of the F alphas are going to be the same because they have the same number here, here, and here. But that's just because we have a really simple example. If we had a different number of rows and columns or whatever, we could have different numerator degrees of freedom, and we'd have to do 3 separate lookups. Okay, so these could be 3 different numbers, but in this case, they're going to be one number for all of them. Right, so if we look at our table, where's the F table? We had that earlier somewhere. That's Q. Here's F. Right, so the degrees of freedom for the numerator is 1, and for denominator is 16. Oh, this cuts off. Sorry. Maybe we have the maybe we have a bigger one later on. Let me scroll down. Do we have the bigger one? Yeah, here it is, right? So we're looking at 1 and we're looking at 16, right? So we got the 4.49 and the 8.53, right? Depending on whether we have alpha equals 0.05 or alpha equals 0.01. So 4.49 or 8.53. Let's just assume we're doing alpha equals 0.05, just because that's the standard, right? Then we get 4.49. And it's the same for each of these. Right? If they had different degrees of freedom, then when we were down here, right, we would have different columns to look in, right? Like for this example, I just showed here, right? We'd have columns 3, column 2, and column 6. Right? We'd have like this column and that column and that column, but they would all have the same denominator degrees of freedom, whatever that happened to be in that case. Okay, so we get the same critical value for each. Now these ones are less and this one's more. So what does this mean? This means that we are not confident enough to say that gender has an effect. We're also not confident enough to say that violence has an effect. But we can confidently say that there is some interaction between gender and violence that gives us an effect. Right? So what's happening here is probably something sorry, I'm saying gender and violence. That's not the example we're doing. So I was still thinking about the previous example. Right here in this example, we're not doing gender versus violence. We're doing time control, self-regulated versus fixed, and text presentation mode, paper versus computer screen. Right? We are looking at learning performance. Right? Does learning performance depend on whether the students have a self-regulated time or a fixed amount of time? And does learning depend on how they receive the text, via paper or via computer screen? And what our results showed is that text on its own does not seem to have an impact that we can be confident in, right? Like we've not rejected the null hypothesis. We don't have enough evidence to say that text presentation mode has an impact, right? Same thing for time control, right? We don't have enough evidence to say that whether students are self-regulated or study for a fixed time period has an impact on their performance. But what we can say is that there is an interaction between these two things, right? That the text presentation mode has a greater impact for one group than it does for another. Right? And if we look at the actual means, right, the means here are 8 and 9 and 9 and 5, right? We can see that the text presentation mode does not seem to have much impact for the students who are studying for a fixed period of time, only going from 8 to 9, but has a much bigger impact for students who are being self-regulated, going from 9 to 5. All right, so that's what we found. And, you know, we might try to figure out why that is at this point, right? We found something and we want to understand it, right? So maybe we need some more research to look into why is it that when students are self-regulated, the text presentation mode has a bigger impact than when they're studying for a fixed period of time. That seems strange, right? But that does seem to be what's happening. Right, so we could go ahead and we could try to figure out why. Right, and then this says we can use alpha. Oh, sorry, I forgot this is alpha equals 0.01. I didn't see that part. So I guess we should have used 8.53. It wouldn't have changed. It wouldn't have changed anything, right? Because these are still not significant, and the last one is still significant. Right, this is for 0.05. This is 0.01. Right, so either way, we have two not significant and one significant. Right, and so these are, this is the thing we just made. Right, these are the numbers we got. All right, and that's, what we get for our hypothesis test. All right, so for our three hypotheses, which were way back up here somewhere, right? These ones, right, we did not reject. Right, we don't have enough evidence to say that factor A makes a difference. Here we do not reject. We don't have enough evidence to say factor B makes a difference. And then here we reject. So there is an interaction between the two factors. All right, and so this kind of wraps up all we're doing here with this. We're not doing the post hoc stuff here. The post hoc stuff gets more complicated, obviously, as the test gets more complicated. It still exists, right? We're going to get computers to do that stuff for us if we want, but when doing it by hand, we're not going to do the post hoc stuff for this. We could also imagine a repeated measures thing, right? What if we tested the same group of students under these 4 different conditions? Said, hey, student, how do you do with paper self-regulated? How do you do with computer self-regulated? How do you do with fixed paper? How do you do with fixed computer screen? Right? Test the same student under all 4 conditions. Do that for a bunch of students. And then this picture up here where we split the between variance treatments, we could also split the within variance treatments, right? This is also possible. It's also something we are just not doing by hand. All right, but a computer can do this and there's no problem, right? It just splits this the way we learned how to do with the by looking at all the different totals for each person and squaring them and so on. And then we have the error thing, which becomes our denominator. Right, so all the post hoc repeated measure stuff that we've done for the 1-factor ANOVA is also possible for 2-factor ANOVA. It just, it gets more and more complicated the more things we add, obviously. Okay, so for your midterm, I have more information on your midterm now. We're going to be doing a big midterm review next class when I see you in person on Monday before reading week. But just to say it here right up so everyone knows, you will have to do independent measures ANOVA, a repeated measures ANOVA, and a 2-factor ANOVA on your test. You will have to do, for the first 2, you'll have to do a post hoc test, right? So maybe for the repeated, you'll have to do a Tukey, and for the independent, you'll do a Chaffee, or maybe the opposite, maybe the reverse of that, right? But for those ones, you have to do a post hoc. We're not going to do a post hoc for the 2-factor. But you can expect all of those things on your test, along with some probability stuff. And that will be your test, right? So your test is going to be those 3 big ANOVA questions, and then some probability questions. Okay, so you'll have to know how to do all of those things. Independent measures, repeated measures, and 2-factor ANOVA, and understand how to do the post hoc tests for the independent and repeated measures ANOVAs. But not for the 2-factor. You don't have to get into that. All right, so this is the end of part 2. Part 3, I will be doing SPSS. So I will see you again when I do part 3.